Going. Okay. I'm Barack. I'm on the paper web platform team. Yeah, so WebGL, it's a very scary thing, but I'm going to try to shed some light on how we can use it in fairly basic things, low-level drawings, and also at the end, we're going to do a fun demo. We're going to recreate a game using 3JS and some physics engine. So yeah, let's get into it here. So this is just kind of an overview. I'm going to go over some really easy to use libraries for 3D work using WebGL, and also the physics library called useCanon. So I have a couple links here. I guess I'll put them in the Zoom chat, but one is an editor where you can, a lot of stuff has been abstracted for you in terms of like how to code WebGL stuff. So it's pretty useful. How do I chat? Okay. So that's the editor. If you want to like follow along, feel free. And this is the starter repo for the demo at the end. So yeah, check that out. Cool. Let's see. So what is a shader? Shader is pretty basic thing. It's essentially just a set of instructions that execute for every pixel on your screen. So the difference, I would say the biggest difference between shader, like anything on a GPU versus CPU, is parallelization of threads. And essentially when you execute each thread, they don't have an idea or a notion of what's going on in any other thread at any other time. So if you think about like the use case of an 800 by 600 screen, you have 480,000 pixels that have to be processed per frame. So if you have like, trying to get like 60 frames per second, you know, that's a lot of pixels to push. And then that's a lot of calculations per second, obviously. So now we have like modern screens, which are way higher quality, and we have way more calculations to do every second. So that's why, you know, GPUs are coming in handy nowadays, and a lot of more processing power can be done on GPU versus the CPU. So GLSL is actually a spec that's adopted by multiple platforms. WebGL just happens to be one of them for the web. And the spec is the same across platforms. You'll see it used in processing. You'll see it used in Unity. There's a bunch of different languages that have GLSL integrated into them. And in the case of the web, you can use the context of WebGL using a canvas component, as you see here. Instead of like, I'm sure a lot of you have used Canvas before. Generally, you use like the 2D context to draw things, and that has like an API on its own, and that's actually executed on the CPU. But if you want to do GPU processing, you can actually use the WebGL context like you use here. And yeah, so if you've ever seen like shader code, you've noticed that there's generally two kinds of files that are associated with shaders. Vertex shaders or fragment shaders. So the big difference here is if you look at this image, essentially the vertex shader will take in, vertex shaders are always executed first. They take in vertices as the inputs along with uniforms or attributes, and transforms coordinates into a value for the fragment shader to use to actually generate a color for that pixel. So this is basically a high-level overview. And then fragment shaders, essentially, yeah, they take the vertices, the transformed vertices from the vertex shader, and create a color output for that pixel. I'm primarily going to be using fragment shaders for all these demos because vertex shaders, I mean, you can do cool things with them, but right now I'm just trying to focus on really simple overview of shaders and GLSL. So yeah, I guess a little bit about why it's so difficult. So personally for me, I think whenever I'm writing shader code, the biggest problem is debugging. It's not something where you can like inspect element and figure out what's happening. It's basically like you get one kind of like dump of a log whenever you get an error, and if you're lucky, you'll understand what it says, but usually it's like guess and check game. You can't print anything, which is horrible. So it's pretty time consuming, and it's really hard for beginners to get into writing like shader code. There is this tool called WebGL Inspector that someone created. I haven't checked it out, but I heard it was actually decent for debugging. So if you want to check that out, it might be interesting. Yeah, but like I said before, it's each thread is has no memory or any kind of a notion of what's happening in another thread. So if I'm drawing one pixel red, I won't know that that pixel is red in the next pixel that I'm drawing blue, for instance. It's all based on the uniforms that you're passing in or the varying attributes that you're passing from the vertex shader. So, and then of course, you know, you have the whole issue of like it's kind of like C, and the syntax is just, you know, not fun for especially like web developers who are used to JavaScript, CSS, etc. So yeah, on the right of my screen here, I have a really basic hello world, and I'm going to go through and describe what everything is, what's happening here. So first thing you'll notice right off the bat is, like I said, it's like it's C-like language. So you have, you know, void, you have types. Everything in the shader world uses float precision. So whenever whenever you're declaring like a vector, you will want to always, you basically always have to use decimal points. This is because the spec of GLSL doesn't guarantee casting between whatever platform is using that spec. So essentially, if I did this, well, this might be too friendly, but if I was actually writing shader code directly, it would error out. So also just to note, in this editor, you will have three variables that are passed in. And essentially it's the resolution of your canvas, where your mouse is located when hovering over it, and the time that's elapsed since the shader has started executing. So these three variables combined, you can actually do a lot of fancy things, and I'll show you soon what I mean. This thing at the top is essentially just pre-compilation conditional operations. So in this, I'm just saying I want the precision of floats to be at a medium level. So you can also do this like high quality or low quality. I mean, it doesn't really matter because we're doing basic things, but you can change that if you want. Yeah. So like in this example, I'm basically just creating the color purple. As you can see, like this is this is basically a vector of decimals between 0 to 1. So you can describe any color like this. You can do blue. Let's see, pink. It's like, so if you think of this as like RGBA, so you have like the first values, red, green, blue, etc. You understand. Pretty straightforward things. This is when you're assigning to GLFrag color, you're essentially saying this is the output of this pixel. So you'll see that a lot when you're trying to get the results you want. Yeah, so I went over this. Uniforms. So a uniform is essentially a variable that is passed in from whatever process is executing that shader. So in this case, with this editor, we have these attributes that are passed in automatically for us. This is not, I mean, obviously you wouldn't have this unless you coded it yourself. But you can do other things that I'll show you later that give you cool results. This is basically the primary way of passing data into a shader. You have uniforms and varying, which is passed between the vertex shader. There is no other like notion of memory unless you're using WebGL 2, and then we have some other fancy things, but in this case, this is all we have. So yeah, cool thing about this is we can do like GPU accelerated functions, like all of these mathematical functions that you would see in JavaScript traditionally is, instead of executing on CPU, you can execute on the GPU, and it's super fast, and you can do cool things like this. So if you get the time that's elapsed, you can do, yeah, so it's like fading, because if you know how the sine function works, as you continue on the x-axis, as for time, you'll interpolate between 1 and 0. So you have this cool like little animation thing here. You can do, I mean, you could do it for all of them, and you can get like cool little colors fading in and out. So pretty neat stuff. Let's see. Yeah, so now I'm going to talk about GL chord. So this is essentially a varying variable that's passed in by the passed into a fragment shader. So in this case, it would be accessed like this, and essentially it's a vec2 type of x and y coordinates of where your current pixel is, the current pixel that you're trying to color is. So generally what people will do is, in order to normalize coordinates, you'll do something like to st. So this will actually give you a normalized coordinates. This is what you would need to do if you want it to be the correct resolution for the screen that you're looking at. So yeah, for example here, oh, I got mixed up. Yeah, so we're normalizing coordinates here, and then we can use that to create a color. So if I use those, if I use these, this variable for the color, you can create a cool like UV map of your pixels. So essentially what I'm doing here is saying, use the position of the pixel on my screen to color the color that it's trying to output. So with that, you can get this like neat like gradient color thing, which is like essentially using the X and Y. We could flip them even and get something else probably. Yeah, just rotate it. So that's pretty cool. This is like pretty low level stuff. I know it's like I'm just trying to do low level stuff, and I'm gonna do some fun high level stuff. So this is the boring stuff. Yeah, it's pretty straightforward. We did this. So yeah, drawing stuff is, as you can see, is it's different than like CSS. It's like very mathematical. It's very low level things that are not generally straightforward for people writing shader code for the first time. So in this example, I want to draw a square, which would be pretty easy in CSS, and then in GLSLU, it's a little bit more different. So I have this pseudocode here. It's essentially describing a stepper function. So if you have some kind of graph paper, if you can imagine some kind of graph paper in your head, if x is greater than 1 and then y is also greater than 1, then you paint it white, which is the color of our square, or else you would paint it black. So this is basically the pseudocode of the square we're going to draw here. So, right, step. Okay. So we have our normalized coordinates. So what we want to do is use the step function, which is built into WebGL here. Let's see. So I'll describe what I'm doing here. I'm not going to have enough time for this stuff. So basically what I'm doing here is setting a vector of color to 0. This is going to be our background color. And using the step function, I can create, I can use a logical, like an AND operator, which is like multiplication here, to create edges here. Let's see. Oh, my bad. This is supposed to be. There you go. So yeah, so you can see that using that logic that I said before, the pseudocode, using the step function, this is basically saying anything past 0.1 is a truthy value or true value, versus if it's under 0.1, it's false value. So using that and an AND operator here, we can create the corner of our square, the left and the bottom here. So we can do the same thing for the other sides. Pretty straightforward. It's just the way you go about drawing things is, I mean, it's different than if you were in the CSS world. Let's see. Oh, these are those. Yeah. So yeah, pretty simple, pretty straightforward. I have also, if you look at the tabs of this editor, I have some pre-made examples that um, I've talked about in the presentation, so you can like click through them if you ever want to look at them. But the cool thing about this editor is you can also like click onto each number and like adjust it and see how it updates. This is really cool for like colors and stuff, but you can see like how it changes the output pretty like immediately. Cool. Smooth step. I'm gonna skip this just for time's sake. So yeah, so we can do like simple edges with the stepper function. So now I'm gonna describe how you do a circle. So circles are a little different because you gotta think of it in terms of like some kind of distance algorithm to return. It's basically like really simple algebra, but you can't use like Cartesian coordinates in this case. So we can use two ways. One way is to use a length function, which is built into WebGL. So I'll show you that. So this function here is essentially just anti-aliasing. Um, so when you draw a circle and you're trying to get the quality of it to be, if you don't want the edges to be really rough, you're going to use the smooth step function to create anti-aliasing in this case. It's just one method to do anti-aliasing. There's plenty of others, and WebGL 2 adds even more, but this is a pretty like crude method of doing it, and I'm just doing it for the sake of this example. Um, so yeah, this circle function is essentially just saying, is creating the distance function. What's that? Right. It's basically just Pythagorean theorem here, which is, high school math, but it comes back to use again in WebGL worlds. Again, because, we're really low level and we don't have access to all the fancy things that we would in maybe CSS or SVG worlds. So yeah, we have this circle here, and so you're probably wondering like how you can use this to draw something. Let's see. There you go. So what I basically did was assign the output pixel to this circle function that I've created here. And the inputs are pretty straightforward. This is just your normalized coordinates. This is your position where you want the circle to be. So you can actually like, move it around if you want to see what you can do with that. You can also change the radius here. So yeah, I can actually
All right, I just messaged him on Zoom to let him know that Zoom froze. So hopefully he'll be back in a moment.
So cool. Let's see where. Okay, yeah. Well, I'm gonna, yeah, circles. I'm just gonna skip ahead to the fun stuff. Matrix transforms. So we can do cool things with matrix transforms. So in this case, I have this uh, uh, initial code in the editor. If you click on animations, if you can follow along here. This is just a simple shape I drew with a couple functions that I found online. And I'm just going to show you an example of what we can do with like really simple matrix transforms. So first thing we can do is we have these functions here that can rotate and scale for us. So we can do a simple scale if you uncomment this code. You can see that we use the output of the sine function to change the scale of the cross. And this is really cool because it's also smooth because sine waves give us a really like natural animation, and we can change it to cosine or whatever you want. But you can make really cool things with this. And the 0.5 that's being added and subtracted is just to center the scale. So this can, if you removed it, you can actually see that the scale is done from a different origin, which in this case I guess is the top right. But the ST is, obviously the normalized coordinates we're using in this pixel. So when we're adding and subtracting 0.5, we're centering it since it's between 0 and 1. So it's cool. We can rotate it. Same exact thing. All you gotta do is just normalize the coordinates. You can actually do this at the same time here. Normalizes the origin and then pass it to this rotate function, which creates a matrix transform and rotates our cross. Let's see what else. Oh yeah, this can be also a sine, so it can interpolate between 0 and 1. So you can do a back and forth animation. Pretty cool. Then we can also do fractional. We can do fractional transforms on it, so we can actually multiply it. The frac method essentially just returns whatever is after the nearest whole number. So we have basically this effect of like creating multiple views of our standard coordinates or normalized coordinates. You can change this number as well and see how it multiplies. You can actually make this sine as well. Oh, that's pretty extreme. Yeah, so you can do cool things like that. You probably want to do this in between the, yeah. Oh, no, that's weird. Yeah, you would need to normalize the origin to do it from the center, but yeah, it's cool things you can do here. I'm gonna comment that out. You can do a simple translate as well. So you can move it. In this case, I'm doing a sine and cosine, so it has like a circle translate, which is pretty cool. So yeah, you can mess around with this. You can do cool things like, yeah, you can like change the values to see how it moves. Yeah, it's pretty cool, and it's super low level and super fast because it's on the GPU. So yeah, this gives you kind of an idea of what you can do with like raw, like low level WebGL. And I have other examples here. This is an example of generating noise based on fractal Brownian motion, which is a function that gives you essentially a random number, which gives you this cool kind of like, it's used a lot in video games, especially to create like clouds. It's used to create like terrain generation. There's a lot of cool things you can do with this, and it's a really like natural like looking thing. And you can also change the octave of it to create like something that kind of evolves over time. And in that case, I have like this here. It almost looks like, it's really cool, neat looking thing. It's essentially just fractal Brownian motion, but you're evolving the octaves, and you can see it kind of changing over time. And the code, I didn't write this code. This is all copied from this online resource that I'll show you later. But it's pretty cool kind of effect you can make. this is something I made before, and this is essentially just using simplex noise. A lot of this is like buffer code, and the real kind of like meat of what I'm doing is if you look at the main function. And yeah, I mean, feel free to dive into it. It's pretty cool stuff. You can make cool looking things. This was my Zoom background for a while, which was fun. But yeah, this is kind of like the core of what I'm getting it from. This is just the noise printed straight to the screen. So you can use this noise to create like a lot of cool things. It's just basically up to your imagination. And then I have like basic shapes if you want to take a look. And yeah, I'm going to get into Three.js before I run out of time. So yeah, Three.js is essentially a 3D library wrapper around WebGL. It makes your life a lot easier. You don't want to write a 3D engine in WebGL, you will hate yourself. Or maybe you won't and you're really smart, and I'm not going to doubt you, but generally most people will use like some kind of library around WebGL, and Three.js is usually most people's choice. So I'm going to show you an example. We're going to create, so this is an example of React 3 Fiber, which is a wrapper on top of Three.js that gives you React hooks for Three.js objects and cameras and lights and everything. So it's super straightforward. If you know, I'm going to guess most people know React here. Really straightforward. You can use JSX. You can create a canvas, you can create lights and props, or I mean, it's super straightforward to use. And using this, we're going to create a cool little game. We're going to create Pong. So this is kind of like a demo of what we can end up with. Let me show some links. I gave the starter, so if you clone the repo, feel free to tag along. If not, it's cool. I'm going to show you everything here. Cool. Let's see. Cool. So yeah, this is pretty simple. Create React app. Yeah, we don't have anything anymore. So starting from scratch. Sorry, give me 1 second. Cool. So I have, the repo is pretty flat. I mean, I just have like a store that lets you add to the total count and does all that silly stuff that you don't want to worry about, and essentially just the wrapper to do all the like the fancy menu stuff. So we can go ahead and start with so we want to set up our scene. We want to do some kind of lighting, and the cool thing about React 3 Fiber is we can just write inside here. We can do ambient lights. Oops, not that. Could do, so let's do our ambient light, let's do our point light here. And let's do our directional light. These are all different. I mean, if you ever use like 3D modeling software, these are just different kinds of lights. And you can, if you go to the Three.js website, they have like all these cool examples you can look at if you want to see how, you know, different objects are used and how they're different. So yeah, so we don't have anything right now because we haven't created like a background. So we'll go ahead and do that. When you use React 3 Fiber, you can create meshes directly like this, and So what we want is we just want a simple plane that just goes on the back of our scene here. Pretty straightforward. And this is just the color. Um, So we have this background. We can just use it like a component. You would just render it inside JSX here. I'm missing. Might need more lights. Maybe. Interesting. Live demos are fun. Okay, I'll just keep going. Hopefully something comes up. But essentially, I'm going to go integrate. So Canon is a physics library in JavaScript, and there's a wrapper written around it for React. It's called Use Canon. Super straightforward to use. If you know Canon, it's easy to use because it gives you really easy to use React's API. And I'm just going to copy and paste it here, but I can describe what's happening. So this is essentially creating a physics world, and all these properties are just representing things like gravity, friction, like stiffness, and these can be adjusted to whatever you want, but it's, in this case, for this example, maybe you can change like the difficulty of the game, or you can change, I mean, the possibilities are endless, but in this case, I'm just gonna have these preset constants. Let's see. Oh, cool. So we have something now. Just double checking that I'm not missing something. Okay, cool. So now we're gonna do, so we have two things in this game. Let's see if I can bring it up again. We have two things, we have the ball or the paddle, and essentially you want to create two kinds of boxes to create the collision effect in this case with the physics engine. So I already have the model of the hand and the paddle in a GLB file. And I already extracted kind of like loading that in the paddle model file here. So you don't have to worry about that, but we can import it here. So going back to our, all right, you need to wrap this in suspense. So whenever you, the way React 3 Fiber works is whenever you load in files, you need to load them with suspense because they're async here. Something is weird about. Give me 1 second. Okay. Where were we? Okay. Suspense. We have that. We don't have the ball yet. We did have the backgrounds. And we have our paddle. So yeah, as you can see, nothing's happening. So this change here is done in scene. That's just basically rotating the camera. But what we want to do is we want to move the paddle with our mouse. So in order to do that, we're going to use linear interpolation between our mouse's X and Y and the position of the model of the hand and paddle in this case. So let's do that here. First thing we want to do is create refs for the objects we're going to move. So we're going to have actually two refs. One will be for the object, and one is going to be for the use canon object that's wrapping our paddle and hand objects inside paddle model. So use box is essentially creating like a physical object inside of our physical world. So as long as you have it something rendering under the physics, a top level of physics parent, you can have attributes using use box. So in this case, we want to create some kind of collision effect with our paddle and our balls. So yeah, these are just like preset for friction, weights, and the spec is all aligned. So if you want to see what is happening here, you do also get these callbacks here. So let's see. Nothing's happening. So now we have our paddle, we have our box set up here. If we get a collision, we'll get an alert box. So let's let's do the ball next so we can. Okay, cool. Ball. So our ball is really simple. It's just a sphere. Everything in the 3JS world has two properties. One is the geometry and one is the material of it, the geometry. And both of those are bound to a mesh object. So every time I'm defining an object in 3D world, I need to represent these two properties to get the look I want to get. Cool. So okay, cool. We don't have material yet. And this is just like, so I'm using a physical material to give that glossy like ball, the glossy look on the ball. There's different kinds of materials in 3JS. You have, let's see, you have standard materials, you have basic materials, you have Lambert, you have physical. There's more in the docs, but they're essentially different methods of representing how materials interact with the world in terms of lighting, shadows, and etc. So in this case, I'm using physical material to give that glossy, like clear coat look. Okay. Okay. So there's our ball. It looks kind of weird. Oh, I see. It's just. Yeah, it looks kind of rough. Oh, it's because our geometry. So when you create a sphere buffer geometry, you want to define how many how many vertices it has. So in this case, it's defaulting to a really low number. So we want to bump that up to like 1,000, for instance, should be better quality here. Uh, oh. Oh, sorry, that's the size. Why is it so? Oh, my bad. I'm get the wrong thing. Sorry. The way it works is the arguments is one is radius. The first one's a radius. The second one is the quality. So the first one will be small. We want 0.5. And if you want like a bigger ball, you can do 1. It really depends on. So I mean, you could do a lot of things with this, right? Maybe the ball gets smaller over time as you play or whatever. You could make it like huge just to see. You could do a bunch of things. In this case, I'm just going to go with 0.5, just some kind of realistic value for. Or I might do 1. It's really small. Cool. So yeah. Next, so we don't want it to be shown when the welcome screen is showing up, so we can hide it here. There's no welcome screen. So you can see it's not falling because we don't have a physics object around it yet. So we can use this simple function in useCanon called useSphere, and that will provide us with kind of like the physical reaction we want it to have. Oh, okay, now it's inside my paddle. All right, that's great. So when you use a useCanon hook, you can set it to initial attributes for the mesh. So in this case, we want to put it up a little bit. So I'm going to bump up the y value. Okay. So now that works, but now we don't have gravity. So we can add mass. Oh, there you go. So we get a collision here with the alert. So this seems to be working. It's cool. Let's see. Let's make that ball smaller. So on collision, all we want to do is just you call the API back and make so in this case, I have a sound playing whenever you the paddle hits or the ball hits the paddle. So you could just run Tong. Oops. And you can get the velocity from the contact here. And this is just to make the sound pitch change depending on how hard it hits. Let's see. Cool. Well, this is pretty easy, but because we want to now let the user move the paddle with the mouse. So that would be what we do next here. So going back to paddle, so what we want to do is interpolate between the x and the y values of the mouse and the position of the object. So in order to do that, we're going to use this. useFrame is essentially a hook that is called on every frame execution of the main 3JS scene. So this is passed in from 3JS Fiber, and this essentially allows us to, if I was going to log, it would just log on every tick that our game is running at. So in this case, we just want to essentially, I'm going to copy and paste for the sake of time, and I'll describe what's happening here. So what's happening here? I created a ref to get the next value of the interpolation that I want. And to create the smoothing effects when you're doing any kind of transition, you can use a lerp function. So what I'm doing here is I'm lerping between the value that we have and the next value that we want. And this third value is actually the amount of easing that we want. So we could actually change that to like 1, and it would be very fast, instant. It just kind of depends on what kind of, see, it's really snappy. Depends on what kind of easing that you want. In this case, we're going to do a 0.2 is usually a good number. And then we also have the, what's this for? Oh, this is setting the box value of the Canon object that we created. And this is just the rotation. So same thing, just changing the rotation as we move the mouse. The last thing we need is the game to be over when the ball hits the ground. So to do that, we can just create a fake plane on the ground that doesn't have any kind of material associated with it, but it has a collision effect that we can add with use Canon. So in this case, create a mesh. This is where so it's going to be under, so we want the y to be negative in this case. Let's see. Okay, so it seems like, hold on, let me refresh. Okay, so it seems like it's instantly colliding, which is not good, but let's see. Oh yeah, we need to rotate it as well. Forgot about that. Because it's right now, it's like, if you can see the webcam, it would be like my hand. We want it to be like this. So we would rotate it on the x-axis. All right, yeah, so pretty much done. When the ball hits the grounds, this callback is called on collision. And all we want to do now is just use the API to end the game. So let's see. All right, yeah, that's it. So now we have a functioning game, and the cool part about this is you can tweak the gravity, you can tweak the friction, you can tweak the mass, you can make things change over time to make the game harder. I also have, if you want to make it look fancy, well, I already added it here, but there's some post-processing here that I'm also adding. So if you look inside post.js, I added a bunch of like examples, but you can just comment them out and you can see how it changes the game. So see now it's like pixelated. So this is all from processing.js, which is a library that gives you all these post-processing abilities, and you can do really cool things with it. So yeah, feel free to just poke around in there. My personal favorite is the glitch one. You can see. You gotta do constant wilds. Yeah, so yeah, you can do fancy things. This is maybe a little too much, but yeah, feel free to just like mess around with that. It's pretty fun. Yeah, that's about it for the demo. Yeah, I mean, there's a couple things I've made. I'll send a link to this paper doc, but pretty much like cool things you can do. This is all WebGL. It's just like messing around with gradients, and I can have like an export function. You can export it, save it. This is also another example. This is fractal Brownian motion again, just like my version of it. So you can like adjust these things to make cool like visuals. I don't know. It's just interesting to me, and it's like all for math, which just makes it even cooler. So yeah, here's some more learning that if you're interested in this stuff, definitely check out. My personal favorite is Book of Shaders. That's how I got started earlier last year. Shader Toy is a really great resource. I think like Dribble for shaders, it's really cool. People make the craziest things in like the least amount of code. It blows my mind. Um, yeah, there's a bunch of stuff in this paper doc, and these are like the libraries I really like. Personally, I really like the wrappers around React too. It just makes everything super easy to write. I just have a couple like tweets I want to show, which is this is someone using like a physical like controller to change how a shader looks on the web, which is super cool. There's a library called MIDI Guyver, which lets you take the input variables from MIDI devices to GLSL shader code. So you can, I mean, the possibilities are endless, and I feel like, you know, this is like the future of the web. Obviously, you know, there's so many cool things you can do, and as GPUs get better, you know, it's only going to get better in terms of like processing power, what you can do with it. And there's also WebVR, which combined with, you know, the stuff I'm doing here, you know, there's even cooler things you can do with WebGL. So yeah, um, that's pretty much it. But I know there's a lot of stuff, but I will link this paper doc in the chat, and then I'll take some questions for the next minutes.
I had a question about the tags, like the mesh.
Yeah.
Normally in React, if it starts with a lowercase letter, it's like native, but you have lowercase things that I think aren't native. Do you know how that works?
So that's all in React 3 Fiber. I should have clarified that. So as long as it's underneath the top level objects of a canvas, which is actually, if you look in scene.js, I have a canvas object. So if it's underneath that parent, you can use these. For some reason, they chose to do the lowercase spec, but I guess it's nice because you don't have to import them. So yeah, that's basically just how React 3 Fiber works. You can probably explicitly import them as well. I'm just not sure. I've just done it this way it's just easier.
Okay, cool.
Yeah.
I just didn't know that was possible.
Yeah, I've never seen it in any other library. It's weird, but I'll have to look into it. It's kind of cool though. Yeah. Anything else? Questions?
All right. Well, it seems like we don't have any other questions. I don't see any in the chat. Oh, wait, I do say, isn't the ball color lacking one hex value?
Oh,
what was that about?
Possibly. I don't know. I was speeding through it. It's probably, I mean, it's in the, if you look at the repo, it's the final version of it, but let me see. Probably missed something here. Oh yeah, it's missing something. I don't know.
Oh, okay. Yeah.
It's just like, okay, yeah, it's just an orange color, so makes sense.
Okay, cool.
Yeah.
Well, thank you for your presentation. It was great. I learned a lot. So.
Awesome. Thank you guys for listening. This was really fun. I love learning about WebGL, so I hope you guys, you know, pursue it. It's really interesting stuff. Cool.
Bye.
Awesome. Oh, I just realized I was cut off the whole time. My webcam. All right. See ya. Thank you guys.